To finish with a series of videos on sequences, we're gonna learn about a very important one called the Fibonacci sequence. This sequence was first discovered by Leonardo Bonacci. He is also known as Fibonacci. That comes from the Italian Figlio di Bonacci. That means son of Bonacci. He was a very famous mathematician born in the 1170s and who died in the 1250s. And he discovered the Fibonacci sequence when studying populations of rabbits and how they were reproducing. And this sequence starts with 0 and the first number is 1. Then every subsequent number is going to be the sum of the previous two. So if 0 is f0 and 1 is f1, then f2 has to be the sum of 0 plus 1, and that is 1. Then f sub 3 has to be 1 plus 1, 2. And then you'd have 3, then 3 plus 2 is 5, 5 plus 3 is 8, then you have 13, and so on. You get a sequence f sub n. So what this sequence has, as we said, is that f2 is the sum of f1 plus f0. f3 is the sum of f2 plus f1. And so fn is the sum of fn minus 1 plus fn minus 2. So the way we can define the Fibonacci sequence is saying that f0 is 0, f1 is 1, and fn is fn minus 1 plus fn minus 2 for all n greater to 1. Now clearly this sequence goes towards infinity because every time we are adding a number that's greater than 0. But what's important about this sequence is not its limit, but the limit of fn divided by fn minus 1. So we're going to try and calculate this limit, and for this we're going to let this limit be L. So first let's work a bit on this expression. We have fn divided by fn minus 1. We want to find the limit L. So all we know is the definition of the sequence. So we just replace it here and we get that fn is fn minus 1 plus fn minus 2 and all this divided by fn minus 1. We can now rewrite this as fn minus 1 divided by fn minus 1 plus fn minus 2 divided by fn minus 2. So now here we have one number divided by itself. This equals to 1. And on this other expression what we're going to do is substitute the subindexes so it can be easier to see, to visualize it, and so we can simplify it a bit. So what we have is 1 plus, and here is what I'm going to do. I'm going to create another letter, call it k, and this k is going to be equal to n minus 1. So then when we do k minus 1, will be equal to n minus 1, which is equal to n minus 2. And so with this, what we get is we have f divided by f, and now the subindexes will be n minus 2, we said was k minus 1, and fn minus 1, we said it was k. But now when we compare this division with this one, we notice something. We have, on the first one, we have fn divided by fn minus 1, and on this one we have fk minus 1 divided by fk, so it's sort of similar, only one is maybe the inverse of the other one. So what we're gonna do is, we know what L is. We said that L was the limit when n tends to infinity of f sub n divided by f sub n minus 1. Okay, but then again we said that this expression was equal to the limit when n tends to infinity of 1 plus fk minus 1 divided by fk. But now if we remember that k depends on n because of this substitution we did, then we can write this as, I'm also going to use that the limit of the sum is the sum of the limits, so we get that the limit of 1 plus the limit of fk minus 1 divided by fk. And now this limit will be when k tends to infinity. But if we look at this, then this limit will be 1 plus, and this will be the inverse to this one, so it's 1 over L. So then we need to find L such that L equals 1 plus 1 over L. So let's go ahead and find this L. We're gonna rewrite this. L equals 1 plus 1 over L. Now multiplying by L on both sides, we get L squared equals to L plus 1 over L times L is 1. And we can just rewrite this as 0 equals minus L squared plus L plus 1. So now we have to remember the quadratic formula. In this case, we would have that A equals to minus 1, B equals to 1, and C equals 1. And when we solve this using the quadratic formula, we get two results. And this is 1 plus or minus the square root of 5 divided by 2. And these numbers, specifically 1 plus square root of 5 divided by 2, is also called phi, or the golden number, also known as the golden ratio, and it's equal to 1.618 and so on. It's actually an irrational number. And this number is very important in mathematics because it's found many times in nature. And to finish this video, I'm gonna give you a few examples where we can find it. If we remember the Fibonacci sequence, it was 1, 1, 2, 3, 5, 8, 13, and so on. So a way of visualizing this is using these numbers as length of sides of squares. So we start with the number 1, for example. We draw a square of sides 1. Then the following number is also a 1, so we also have to draw the same square. Then the next one is 2, so we have to draw a square of sides 2. We can just draw it here. This is all very approximate because I'm not actually measuring the sides, but there's sort of measure 1 and 2. Then the next one is of sides 3, so it looks something like this. The next one is of length 5, so it'll be something like this. The next one is 8, so we have 2 here, 3 plus 5 is 8. And the next one, and the last one I'm going to be drawing, is the 13. And here we got this rectangle. And this rectangle is called the golden rectangle. And something that's very popular is that if we join the two opposite corners of these squares like this, we get this form that's called the golden spiral. And these forms are found very often in nature. For example, they can be found in sunflowers. When we look at a sunflower, we can find these sort of spirals. But also we can find them in the opposite direction. And the interesting thing about this is that when we count the amount of spirals we have in the sunflower, we find sometimes that the ones in the green direction are 34 and the red direction 55. And in some bigger sunflowers we can find 89 and 144. Now what's so interesting about these numbers is that 34 and 55 are both consecutive numbers in the Fibonacci sequence, and the same happens with 89 and 144. Another very curious thing about the sunflower is, well, the things we see here are seeds for the sunflower. So what happens is these seeds need as much space as possible, but we also want to be as many seeds as possible in one sunflower. So if this is the sunflower, this circle, what happens is, let's say we have one seed here, then if this is like the first seed that grew, the next one will always be at this angle, that is 137.5 degrees. So the next one will be somewhere around here. If this was the first seed to grow, then this one will always be the second one. And then the other one will be approximately here, and then here, and so on. And you might wonder, okay, fine, but what does 137.5 has to do with sunflowers? Well, 137.5 equals to 360 degrees minus 360 divided by 5, by the golden number. And if we think about it, 360 degrees, it's the whole circle, it's 1 unit. And these sort of relations can be found in many other things in nature. So maybe next time you find a spiral somewhere, try and think about the Fibonacci sequence and how you can relate it to math.